Hi everyone, welcome to Science class, Physics Chapter 12, Electricity Part 8. And today's topic is Joule's law of heating and its application. And you're going to even learn in this video about electric power. Let us have a recap of previous video. We have learned about series versus parallel, where we have seen that in a series circuit, the current is constant throughout the electric circuit and potential difference divides across the resistors. So, we cannot connect two or more electric gadgets of widely different current ranges. And in series, if one gadget is not working, other gadgets will not work. In parallel, it is totally different. In parallel circuit, it divides the current, whereas potential difference remains the same across resistors. So, we can connect two or more electric gadgets of widely different current ranges. And if one gadget is not working, the other gadgets will work easily. So, if you connect a parallel connection, easily you can operate every gadget individually. And parallel connection is much preferable in maximum cases. And even you have learned in last video about heating effect of electric current. Now, let us learn much more about heating effect, where you are going to learn Joule's law of heating. Now let us understand the new topic, Joule's law of heating. Consider a current I flowing through a resistor of resistance R. Let the potential difference across it be V as shown in the figure. Let T be the time during which a charge Q flows across. The work done in the moving the charge Q through a potential difference V is VQ. Therefore, the source must supply energy equal to VQ in time T. Hence, the power input to the circuit by the source is P is equal to W by T, which is nothing but work done by time. And here work done, we consider the work done of an electron to move charge from one point to other point. That is the definition of potential difference. So from that, you will get the formula W is equal to VQ. When you substitute, P is equal to VQ by T. Separate V, so it will become P is equal to V into Q by T. And we know the formula Q by T is equal to I. You will get P is equal to VI, which is the power input to the circuit by the source. Now, if I talk about energy that is supplied to the circuit by the source in time T is nothing but power into time. So you know the formula energy is equal to power into time. Let us see what happens to this energy expended by the source. This energy gets dissipated in the resistor as heat. Thus, for a steady current I, the amount of heat H produced in time t is given as energy is equal to power into time. Here energy is nothing but heat energy. So I can write E is equal to P into T. Substitute the formula for P is equal to VI, then you will get heat energy is equal to, that is H is equal to VIT. Now apply the Ohm's law. V is equal to IR in the formula. You will get heat energy, that is H is equal to IR into IT, which is nothing but H is equal to I square RT. This is known as Joule's law of heating. But according to the physics, the definition is different. This is only the derivation of Joule's law of heating. Children, observe the circuit diagram clearly, where resistance R is there and current I and potential difference V is there. Heat produced across the R is given as I square RT. Remember, across this resistance, heat produced can be calculated by using the formula H is equal to I square RT. According to the definition, the law implies that heat produced in a resistor is directly proportional to the square of the current for a given resistance, directly proportional to the resistance for the given current, and it is directly proportional to the time for which the current flows through the resistor. Children, remember The definition of Joule's law of heating, you must write all the 3 points as it is. And in practical situations, when an electric appliance is connected to no voltage source, that is equation H is equal to I square RT, it is used after calculating the current through it using the relation I is equal to V by R, which is nothing but a Ohm's law. Dear students, by using Joule's law, that is H is equal to I square RT, we have numerical. Those numericals we'll discuss in the next video. Now, practical applications of heating effect of electric current. Children, the generation of heat in a conductor is an inevitable consequence of electric current. In many cases, it is undesirable as it converts useful of electrical energy into heat. In electric circuits, the unavoidable heating can increase the temperature of the components and alter their properties. However, heating effect of electric current has many useful applications. Children, you have observed in electric bulb, fan or even your mobile is getting heated up just because of practical applications of this heating effect, which is unavoidable. So that can be useful to generate new components or new electric device like a laundry iron, electric toaster, electric oven, electric kettle, electric heater and some other devices which are based on this Joule's law of heating, where these devices produce only heat. You can observe some of them I have given down, that is electric heater and room heater, electric iron and electric kettle. One of the application is the electric heating is used to produce light, as in an electric bulb. The filament must retain as much of the heat generated as it possible. So that it gets very hot and emits light, it must not melt at such high temperature. A strong metal with a high melting point such as tungsten is used for making bulb filament because tungsten melts at a high temperature 3380 degrees Celsius. Observe the below figure children, where filament in the bulb gets heated up and bulb is glowing. Dear students, the filament what we used is thoroughly isolated as much as possible using insulating support, etc. The bulbs are usually filled with chemically inactive nitrogen and argon gases to prolong the life of filament. Most of the power consumed by the filament appears as heat, but a small part of it is in the form of light radiated. Look at the below figure where argon or any inert gas is filled and the filament wire produces heat and it's giving because of heat light. And remember children, in a light bulb, the heated filament which is also a resistance wire becomes so hot that light is also emitted. So maintaining the temperature of filament is very important and it should not melt. That is the reason the bulb is a very good example for application of Joule's law of heating effect. Yeah, another common applications of a Joule's heating is the fuse used in electric circuits. Fuse protects circuits and appliances by stopping the flow of any unduly high electric current. Solely it is called as safety device. The fuse is placed in series with the device. It consists of a piece of a wire made up of a metal or an alloy of appropriate melting point. For example, aluminium, copper, iron, lead can be used. In the below figure you can observe some of the fuses are shown. Let us understand how fuse works. Children, if a current larger than a specified value flows through the circuit, the temperature of fuse wire increases. This melts the fuse wire and breaks the circuit. And the fuse wire is usually encased in a cartridge of a porcelain or similar material with the metal ends. The fuse used for domestic purpose are rated as 1 amp, 2 amp, 3 amp, 5 amp, 10 amp, etc. You can observe in below figure there is a porcelain holder and fuse wire is shown, as well as a metal holding also is shown. In another side, a figure which is giving an idea about miniature circuit board, which we call it as a MCBs, that also works as a fuse. Now let us understand how the rating of fuse wire we can calculate. Rating the fuse wire depends on how much current flows in any electric device operated at constant potential difference. So, the fuse can be allowed the flow of only required amount of current, not excess amount of current. One example is given below, you can check it out. An electric iron which consumes 1 kilowatt, nothing but 1000 watt power when it is operated at 220 volts. And the rating for fuse wire for the iron box is given. We can calculate by using power formula P is equal to VI, the current. If you understand how much current is required for the potential difference 220 volt and the power of the iron box is 1000, then you can make a fuse wire of a required amount of rating. So when you calculate I is equal to P by V, nothing but 1000 by 220, you got the value 4.5 amp. So iron box must be use a fuse wire of 5 amp rating, and in case if more than 5 amp current is flowing in the iron box, fuse melts and the box will be saved. Let us move to another topic, that is electric power. You have studied in an earlier class that rate of doing work is power. This is also the rate of consumption of energy in case of electricity. The equation H is equal to I square RT gives the rate at which electric energy is dissipated or consumed in an electric circuit. This is also termed as electric power. The power P is given by P is equal to VI, that can be written as, after substituting according to Ohm's law V as IR, you get P is equal to I square R. Similarly, if you substitute I from Ohm's law as V by R, even you can write power as P is equal to V square by R. The SI unit of electric power is watt. Let us define now what is 1 watt. It is the power consumed by a device that carries 1 amp of a current when operated at potential difference of 1 volt. Thus, 1 watt can be written as, or 1 watt is equal to 1 volt into 1 ampere, that is equal to 1 volt ampere, which is nothing but 1 watt. Children, the unit watt is very small. Therefore, in actual practice, we use much larger unit called kilowatt. It is equal to 1000 watts. Since electrical energy is a product of power and time, the unit of electric energy is therefore watt hour. 1 watt hour is the energy consumed when 1 watt of power is used for 1 hour. The commercial unit of electric energy is kilowatt hour, and it is commonly known as unit. 1 unit is equal to 1 kilowatt hour. If I go for converting 1 kilowatt hour is in the form of a joule, even you have learned this one in last year, let us understand that 1 kilowatt hour is equal to 1000 watt into 3600 seconds. When you calculate, you will get 1 kilowatt hour is equal to 3.6 into 10 to the power 6 joules. Children, this ends the lesson. Still there are numerical based on heating effect as well as Joule's law of heating and power based sums. Let us discuss all these numericals in the next video. Now let us move to the worksheet. Worksheet 7. The first question is define Joule's law of heating. Second one, why is the tungsten used almost exclusively for filament of electric lamps? Third one, define 1 watt. Fourth one, what do you mean by electric power? And fifth one, how does the fuse wire work to save home appliances? This ends the video. Take care children. Bye.